All right. Give you guys just a second.
He gets water.
Okay, we have a little demo for class today. So at one point, I'm going to pass something around, and you guys are going to have to be very careful not to agitate it, okay? We're going to pass it gently so everybody can look close, but you're not going to shake it or agitate it because that would kind of ruin the effect. Not Ozzy. We're not passing Ozzy around, though that could be interesting, I swear. I agree. No shaking or agitating the dachshund. We don't do that for sure. He's already been agitated once this year. All right. So are we ready? Yeah. Yeah. Are we good? Are we ready? All right. So today we are going to be talking about how we classify reactions. What kind of a reaction are we dealing with? All right. So let's start by talking about what types there are. And then we'll talk about each type. Drew, you need to pay attention. Okay, here we go. So we have combustion, synthesis, decomposition, and displacement and double displacement. Sometimes people call displacement single displacement versus double displacement. You can do it that way too. And later we'll talk about specific types called a redox reaction. It's we'll get to those. Those get a little more complicated, but these are our basic types. All right, so in a combustion reaction, it's a carbon-based compound, but what's it reacting with? What's necessary for combustion? Colin, oxygen. Okay, very good. So I was talking to the juniors this morning about concentration being something that affects reaction rate. If your reactants are more concentrated, you're more likely to get a faster reaction. So a great example of this is, you ever seen anybody that has an oxygen container that they drag around with them, and sometimes they have like the little nose tube, little nasal cannula? All right, if you have that, Liam, if you have that in your house, you're supposed to have a big sign on your front door that says oxygen in use. Why? Why, PJ? Yes, because it's highly concentrated oxygen, and if it makes its way into the atmosphere during a fire, you're going to have a hugely involved, very fast, very hot moving combustion reaction. Yeah, so the oxygen in use sign is not so your neighbors know. Colin and Drew, stop. The oxygen in use sign is not so your neighbors know. Who's it for? Who's that sign for? Fire. The fire department. Thank you. So I have a friend who has oxygen in use with her children, and she thought the sign looked tacky and she didn't want to put a sign on her door. And I said, no, because my brother-in-law's a firefighter. I'm like, that sign's going on your door because somebody could be in serious trouble without it, right? Right. Okay. So a combustion reaction is going to produce carbon dioxide and at least something else, which is what? Oh, Colin F. Water. Very good. You're going to get water from that. All right. So carbon dioxide and water are going to be produced in a combustion reaction. And when not enough oxygen is available, what do we call the reaction? What do we say? It's what? Anybody know? We're going to say it's incomplete. All right. And producing carbon dioxide and what, as well as carbon dioxide and water vapor? What's the other thing that gets produced? Yeah, can be, but soot is what we're looking for. So soot is the leftover ash part. So remember we talked about, what do I say happens every year when it snows? There's always an idiot that does what? Yeah, lights a snowball with a lighter and says, look, it's plastic, it's turning black, it's soot, because the combustion reaction for the butane and the lighter is incomplete and it's producing soot, and the soot is just collecting on the little snowball. So that's what's happening, right? It's my favorite part of every big snowstorm is searching the internet for who's the new idiot this year, because there's one every year. I love them. They're always fun. They're the same people that are worried about the chemtrails and the whatnots that are showing you the plastic snow. All right, so let's talk about a decomposition. Shh, guys back there, I don't want to yell all day. Let's not. A decomposition reaction. So this is when a compound breaks down into two or more simpler substances. So what kind of compounds typically decompose into two elements? What do we call those compounds that could decompose into two elements? Do we know? So those are binary. It's composed of two things, so it's a binary compound, and it's going to compose into its two elements, right? Decompose. Compounds that are made of three or more elements, how do they decompose?
Into three or more.
Yeah, into it. Sometimes what we call polyatomic ions, right? So if you have a compound that's composed of only two elements, it's always going to decompose into those two elements separately, because that's a binary compound, and that's how it's going to decompose. But if you've got one that's made up of, guys in the back, I will put you butts on the floor right here. Stop talking. So you do not want to sit on the floor like kindergartners, right? Zip it. I'm very tempted. That's for sleeping people, though. Y'all know that, right? Like if you fall asleep in class, that this is how I wake you up. Oh, some of you weren't aware this was back here the whole time. Look at this trigger discipline. I'm not playing. This is how it's back here. Yes. Actually, I hit Sydney one time when I was aiming. Who was I aiming for? Alex, I think, and I hit Sydney. Yeah, I have that. This thing doesn't aim well. I have actually fairly decent aim, not that.
She's almost leaving, aim for the person next to her.
Pretty much. You gotta aim high because All right, so let's now talk about a synthesis. So if a decomposition is something breaking down, then a synthesis is when you have a singular compound that forms from two or more what?
Reactants.
Yeah, two or more reactants. Yeah, exactly. Two or more different kinds of things, or two things are going in and they're making one thing. So those two things going in, making one new thing, is a synthesis. Synthesize means to bring together, right? Like to create. And then reactants are often two what? Two elements or two simple compounds, he says. There we go. All right, so when you have two elements or two simple compounds that combine and they form a new, usually kind of like, you can think of it like a bigger compound, that's your synthesis reaction. All right, now, this is going to be our demo. So listen up. I'm going to make sure you understand what's going on. We're going to pass it around and everybody's going to watch. And then I'm going to sit it up here because it's a slower reaction. It's going to take some time, but by the end of class, it'll be really cool. All right. So an example of a single displacement reaction is what we're going to show in just a minute. So in a single displacement reaction or displacement reaction, you have a single element that reacts with the compound and displaces what? What's it displacing from the compound? Does anybody know? Another element, right? So you've got two things, and we're going to show you an exact example of this in just a second. And one of those things is swapping out for something else. The products are different. What are they? They're a different element, right? And a different compound. Very good. And that's what forms from your reactant. Bam. So metals displace what?
Non-metal.
Metals displace metals. Oops. Metals displace metals and non-metals displace. There you go. All right, that's easy. Metals displace metals, non-metals displace non-metals. All right, so I'm going to show you this particular reaction. We're going to observe. All right. Let's begin by observing. What do we observe in the test tube at the moment?
Air.
Hold on, I'm gonna hold it up. What do we say?
Liquid.
Can we say it's water?
Liquid.
No,
Clear liquid.
it's a clear, like colorless liquid, and it's clear, right? It's not opaque. It's clear. Everybody agrees it's clear? Do we agree it's colorless? Yeah, it's clear and colorless. All right, and what, does anybody want to guess what that is? It's copper wire. Okay, this is just, all this is pure copper wire. I've not done anything to it, but it does not have a coating or anything like that on it. It's just pure copper wire. Yes.
Is it the one that with the sediment from like the liquid goes onto the copper?
Not quite. Okay, so here's what we're going to observe. This is called, it has a name, the copper wire displacement experiment. It's great. It's a standard chemistry demonstration. So we're going to stick this piece of copper wire in this solution. The solution is silver nitrate. So what's in it? Silver and what else? Nitrogen and what else? Very good. Oh, I love it. There it is. AgNO3. That should be a subscript, but it didn't copy that way and I forgot to fix it. So it's going to cause a single displacement reaction where the more reactive metal, what's the more reactive metal going to be? Copper or silver? Copper is more reactive, right? So the more reactive metal, copper, sorry, is going to replace the silver ions in the solution, and your result is going to be silver metal depositing on the copper wire. And then eventually, as the copper ions make their way into the solution is going to change color. And what do you think it will be?
Copper nitrate.
Blue. Copper makes blue. Remember, you used copper sulfate today. It's blue. So the solution's going to turn blue, and then the silver is going to grow. Silver atoms are going to collect on this wire, and it's going to look a little like hair growing on the wire. When you see it at first, it's not going to look super silvery, but over time it will. And eventually, that when I did it last night, just to make sure, I got this much pure silver off my wire, which is a fairly decent amount of pure silver. It's a little bit there, but you could actually see the metal like locking in place and kind of growing within its structure. So here's what we're going to do. I'm going to put it in this beaker. All right. Shh. So that it's easier to hold and nobody drops or shakes it. So I'm going to put it in like this. And then what I'm going to do is I'm going to hook this little wire, see the little hook? I'm going to hook that on the top, and I'm going to put the cork in, and I'm going to pass it around, and you pass it very slowly. Don't shake it. Be very gentle with it. And when it gets to the end, somebody tell me, and then I'm going to put it up here and we're going to watch, and it will get fat with silver, very fat. All right, are you ready? Because it's going to start kind of right away. So I'm going to drop it in, hook it on the side, put in my, stop, put in my cork. All right, you start, you watch it for a second so you can almost see it starting. It only takes a second, so just watch for a second and then pass it around so everybody can watch. All right, so here's what's happening. There's our reaction, okay? That I missed that subscript again. That should be a subscript, that 3. So you've got copper in solid form, and then you have aqueous silver nitrate, right? And it's going to produce copper nitrate aqueous and silver as a solid. And you're going to see it form on the wire. Means it's in solution, right? So the copper wire is going to become coated with a shiny crystalline silver deposit. It kind of looks a little black at first, but you'll see it turn more white with time. And the solution's going to turn blue because it's going to form copper nitrate. All right, so it's coming around. And you can see the copper wire that's not in solution, the stuff that's at the top of the test tube. You can compare that to what's going on in the solution. Can you see it growing in there, Caitlin? Just a little at a time. And I'll bring it down to Asher, and then Addie can pass it over to Colin. Okay, got it. Thank you. Can you see it growing in there? See that growing on the wire?
Yeah.
That's cool, right? Okay, here you go.
It's a big wire.
Yeah, it's making the wire very fat. It's really cool. So we're gonna watch it, and we're gonna pass it all the way around. And then we'll put it up here and we'll watch, and it'll get about the size of a standard string of yarn. It'll get very fat. It's really wild. Like, it can get so fat that you kind of lose the spiral and it almost looks like a swirled ice cream. It's really, really neat. I'm letting everybody get a look at it as it goes around. Ooh. Now here's the crazy thing. After it gets to Drew, I'm gonna bring it back up, and Yusuf, you were the first person to see it. So I want you to compare what you saw to what it's, because it's been what, maybe a minute and a half? Not very long, right? All right, it's coming back to you, Lucas. There we go. Silver, ooh. All right, so now Drew's got the last. Pay attention, Drew. Somebody see it growing? Pretty neat, right? You got it. All right, so, shh, guys, stop. Yusuf, you looked at it first, right? How does it look compared to what you saw?
It looks much better.
Much better,
It looks
right?
fuzzy.
Yeah, it's fuzzy, much better. Okay, so we're gonna put it here. No, actually here, I think you can see it better there. There's some better light there. And this is how much sugar we got, silver we got off it last time, so I'll put that right next to it. After class, you can get a good look. All right. While that grows, yes. No, definitely not. No, that's not good to eat. No, not like that. No, you can eat tiny bits of gold. Like, you can put gold. I mean, you could eat you can't eat tiny amounts of silver. You can also eat tiny amounts of gold. All right, so attention back up here. Goobers in the back. So a displacement reaction that is a double. Remember, this one is a single displacement. The copper is being swapped out for the silver in both the solution. In the solution, the silver's leaving, the copper's coming in, and on the wire, the silver's collecting, the copper's going out into the solution. So this is a double. So in this one, two compounds, what do we want? In aqueous solution, it has to be in solution, okay? Exchange what? Kind of ions. All right, so two compounds exchange ions. What's an ion? A charge, an atom with a charge, basically, right? Okay. And one of the products must be what? Do we know what we get from these? So one of them has to be a solid precipitate, a gas, or a molecular compound. So these are your results with double displacement reactions. All right, so now we have something called the reaction series. Now this shows which of these particular elements are more reactive. And there is a ridiculous mnemonic device that is, please stop calling me a careless zebra. Instead, try learning how copper saves gold. I don't think I've ever been able to memorize that successfully because it's goofy. And you don't have to memorize this reaction series, but it is helpful. Now you can find reactivity charts, which we'll be using in a bit. So yes.
First, why it's missing platinum, I think.
Platinum?
Yeah, platinum.
Yeah, maybe. But these are just like your most common. Like,
and why is carbon and hydrogen on inside parentheses?
I think because they're dealing with oh, that's a good question.
Is
I
it
don't
because
know.
it's the only non-metals?
Yeah, hydrogen being non-metal, but carbon. That's why. Yeah, non-metals. That's it. He found it. It's because they're the non-metals in there. All right. So let's look here.
Oh, wow.
Now we're going to, yes, ooh, pretty. Fancy. So now we're going to talk about writing net ionic equations. Okay, don't be afraid. Don't be afraid. It's numbers. Don't be afraid. Some of you go, oh God, no numbers. All right. We're going to get some help from Professor Dave, our friend, in a bit. But net ionic equations and then complete ionic equations, we'll see how both of them work. So here's what you have to do. Liam, Andrew, what you have to do is identify spectator ions. We're going to talk about those. Write your net ionic equation, and then you have to check atoms and their charges. So what's a spectator ion? It's an ion that what? PJ?
An ion does not take part in the solution, but it's still there.
Yeah, it doesn't take part in the reaction, right? But it's still found in the solution. So a spectator ion stays itself through the whole reaction. It doesn't take part in the reaction, but it remains there throughout the whole time. All right. So we're going to talk about how does that work with our friend, Professor Dave. Hopefully the embedded commercials will end soon, but let's just zip it if they're, oh yeah, here we go. I can't wait for these to be over. Tomorrow can't come fast enough. Yeah.
Don't to the debt.
Blah, blah,
Harris's
blah.
policies would reduce the debt.
And gone. Yay.
Hey, Professor Dave, let's talk about solutions. He knows a lot about the science of Professor Dave explains. A homogeneous mixture that's in one phase is called a solution. Think of something like table salt in water. If we are talking about a liquid solution, the thing that gets dissolved is called the solute. In this case, that's the salt. And the thing doing the dissolving is called the solvent. Here, that's the water. Solutions tend to retain the properties of the solvent, since solvent particles are typically much more abundant than the solute. We can say that a solute is either soluble or insoluble in a particular solvent, depending on whether it will dissolve in that solvent. Something will dissolve if in doing so, it will make favorable intermolecular contacts with solvent particles. In the case of salt, it will dissolve and dissociate so that the sodium ions and chloride ions can make ion dipole interactions with water molecules. A nonpolar covalent compound will not dissolve in water because without a dipole, it can't make any dipole-dipole interactions with polar water molecules. That's where we get the saying, like dissolves like. Salt water is a strong electrolyte because the formally charged ions in solution can conduct electricity. Weak electrolytes only partially ionize in solution, so they conduct electricity weakly. We can use molecular equations to describe substances that transform in solution, and it will be useful to use subscripts after each compound to show its phase. There's solid, liquid, and gas, and we use the word aqueous to describe ions that dissociate in solution. This is important because sometimes ions come together to form a new compound which may be insoluble in that solvent. In such a case, we will denote that it is in the solid phase, as it will crash out of solution as a precipitate. We can write molecular equations to describe solution chemistry, but we can also use net ionic equations. This summarizes the key transformation by eliminating spectator ions, the ones that just sit in solution and don't do chemistry. To do this, we start by writing the complete ionic equation. This involves splitting the ionic compounds into their respective ions. Just remember the common charges of the ions to include the correct formal charges. Subscripts in the molecular equation become coefficients in the complete ionic equation since all the components are dissociated. Anything that's present on both sides, we can cancel out, like an algebra problem. These are the substances that don't do any chemistry. What's left are the two ions that come together to form a solid precipitate, which is a chemical change. This is the net ionic equation. In addition, sometimes we categorize these kinds of reactions as being either synthesis, where two things become one, decomposition, where one thing becomes two, single displacement, where one component swaps out, or double displacement, where two components switch places. This is just good vocabulary to know. Let's check comprehension.
Okay, I'll pause it in case anybody wants to try it, but we're going to do some in just a minute, and we're going to have a reactivity series for you to see and then charges. But if you know how to find charges on the periodic table, which we've done a little, and you might be able to figure it out. So you're going to have to separate out and go away. sodium, phosphate, right? Barium and chloride, sodium and chloride, and barium and phosphate. So he'll show you his answer here, and then we'll do one more video on how to do it, and then we'll try some on our own. Bum, 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 bum. All right, so look what he did real quick. He separated out the sodium and the phosphate, and he noted that they were both aqueous, right? Then he separated out the barium and the chlorine. You got barium chloride there, right? And he noted that they're both aqueous. Then over here, there is your NaCl. So he separated your sodium and your chloride. And then barium phosphate. What state is the barium phosphate in?
Solid.
It's a solid. So what would have happened if you mixed these two solutions together?
Before precipitate.
They're going to form a precipitate. Did you do that in lab today? Yes. What did you mix? Sodium carbonate, and then what? Copper 2 sulfate, right? And you mix them together and you got a precipitate that crashed out of solution. Okay. You have to listen to the rest of the marimba music because it's just too fun. All right, so how do we write them? Okay, here we go. Pay attention. All right, some of you are giggly today because you have had donuts and marshmallows, but pay attention to this one and then we're going to practice some ourselves, okay?
There's no denying.
Oh, not that.
He's the one
Oh, I'm
who
so
has to get
tired of
shots.
these.
But he's got shots. And
Yes.
he'll fight for Georgia with
It's
everything
got
he's
to stop at some point,
He
you
holds
know?
top secret clearance.
Like maybe tomorrow, maybe they'll end.
In this video, we're going to look at net ionic equations and specifically spectator ions.
Pay
So
attention.
by the end of the video, you understand how to do net ionic equations, but you'll really understand these spectator ions, their role in the equations, and really what's happening chemically. So we'll start with a common net ionic equation, silver nitrate and sodium chloride. So here is our silver nitrate, AgNO3, and our sodium chloride, NaCl. Silver nitrate, that's a crystal, it actually looks like a powder here, a white powder. And then sodium chloride, we have these salt crystals here, table salt. But for net ionic equations, they take place in solution, in aqueous solutions. So we need to dissolve these in water for any reaction to take place. So let's do that. So here we're putting NaCl into the water. It will dissolve or dissociate into its ion. So it goes in the water and it breaks down into the Na plus and the Cl minus ion. So these ions are part of our net ionic equation. Likewise, we can add
Listen.
water to the AgNO3, and that'll dissolve and break apart into Ag plus and then the NO3 minus ions. So back to our net ionic equation here. We said Ag plus, NO3 minus, sodium was a plus and chlorine was a minus. And you can look these up on the periodic table.
You see how to do that? Do we know how to do that? Kind of like we were doing when we talked before about ionic compounds. This is back to the ionic compounds, right?
Well, and then for things like these polyatomic ions, you need to look those up on a chart or memorize the NO3 minus the nitrogen.
Just look them up on the chart. No point in memorizing them.
Charges.
Not for this
Simply
one.
dissolve them. So we can put a little AQ for aqueous after each one. And we've got the first part of our equation. In this case, the plus will go with the minus here, and then this plus here will go with this minus. It's a double displacement reaction. That'll give us this. With net ionic equations, you're normally given these are going to be aqueous, so the reaction can take place. But you have to figure out whether these will be aqueous, liquids, solids, or gases. The way to do it, we can look up on a chart that AgCl on a solubility chart, that's going to be insoluble. It's not going to dissolve. So we'll put a solid after that. And then NaNO3, sodium nitrates. Nitrates are usually soluble, or we could look it up. This is going to be aqueous as well. So it's soluble. That means it dissolves and it's aqueous.
So what's
So
your
now we have six
precipitate,
for the net ionic equation.
right?
If you think about this reaction,
Precipitate.
when it takes place, what should happen? The sodium nitrate, that's aqueous, so it should stay dissolved. But this solid, that should fall the bottom of the test tube, that should be precipitated. And that's important when we're writing net ionic equations. So let's look at the reaction and see that happen. So the test tube, that's the aqueous AgNO3, it's a clear solution. In the beaker, that's the NaCl aqueous solution. So we're going to pour the silver nitrate into the beaker. Watch what happens. So that white cloud, that's the AgCl, that's the silver chloride, and it's actually a solid. It'll fall to the bottom of the beaker in a while and just be a white layer on the bottom. The NaNO3, however, that's still aqueous, it's still dissolved. Those are called spectator ions. So back again to our equation. We saw we had these aqueous solutions, we mixed these together, we got a solid, and then we really didn't see anything happen with the NaNO3 because it's aqueous, it's dissolved. From this, we can write what's called a total ionic equation. We basically just write all of the ions, and then any solid, liquid, or gas, we leave together, we don't break it up. So let's write the total ionic equation, and I won't write the states like aqueous and solid until the end. And here we have AgCl, it's the solid. We don't break that up. It does not dissolve, it does not dissociate into ions, it's just AgCl. So think back.
Why are we only writing out the ions that are not solids? Why are we doing that, Jordan?
Because the aqueous ones are dissolved, so they're
Right.
separated, so they're gonna have that charge.
Right, so they're disassociated, they're obviously soluble in the water, in the aqueous solution, so they are just there, right? Okay, so you don't break up any solids. You do break up the rest of your ions.
Back to where we started. We have our test tube, we had AgNO3, it was dissolved, so we had these ions in the aqueous solution, and we had our NaCl, which was also aqueous. When we mixed them together, we saw that white precipitate, that was the solid AgCl. And then the NaNO3, that stayed in solution. This is the total ionic equation, and based on this, we can write the net ionic equation. When we write the net ionic equation, we're looking for what changed in the reaction. So if we think about it, we have NO3 here and NO3 here. It didn't change, so we cross that out. We're not worried about that for our net ionic equation. The Na plus and the Na plus, it didn't change. We look at our test tubes and our beakers, we have Na plus in the test tube, and we have Na plus in the beakers, no change. What did change? The Ag plus, the silver ion, and the Cl minus, the chloride ion, they joined together to form a solid. That's very different. These ions in the water dissolved clear, and then you have this white precipitate. Based on this, we have our net ionic equation, which looks like this. So let's talk about those spectator ions again. These are our spectator ions. They're spectator ions because they just watched. They didn't do anything. They started out as NO3 minus, ended up as NO3 minus. And because of that, they've not changed. So spectator ions, they're involved in the chemical reaction. They were bonded to these chemicals here, but they stay the same at the end as they were at the beginning. Those are spectator ions. So now you should understand net ionic equations and the role of spectator ions. What you need to do at this point is practice. Do a lot of balancing net ionic equations. There's a link in the description.
Which is what we're gonna do. Yay.
Sounded like he inserted that iron. Like,
Oh, go on. Yep.
That iron.
There we go. All right, are we ready to practice? Get your either a piece of paper or your whiteboard out. By the way, while you're getting it out, I'm just gonna hold this up for a minute. Does everybody see? See how fat that got?
Yeah.
That's really cool, right? And you notice the solution, if I hold it against my white cutter, it's starting to change to blue, right? The solution's going blue. And then there's all the silver deposit. And when you guys are done with class, you can get a real close look at it and you can actually see it's glittering. in there.
do want to taste it.
Yes, don't taste it. We're not gonna taste it. It's not gonna be tasty. All right, are we ready to practice? Let's practice. All right, so here's our molecular equation. Sodium carbonate, iron chloride, iron carbonate, sodium chloride. So here's what you need to know. Here are your polyatomic ions that are common. And next to them is their charge and their name. So you can see, for example, right here, see the CO3 carbonate, says it right here, carbonate. And then it shows you the charge is 2-. Does everybody see that? That's how you know the charges on some of these. You can just use a chart. You don't need to memorize polyatomic ion charges. As for trends in charge, for example, your iron and your your iron, where'd it go? Oh no, that's over here. Your chlorine, there's your chlorine, right? So you can see what the charge is on that based on this. This is solubility chart. So remember, if something is a solid, then you know it's not going to be part of your solution. Here's your iron. It's a 3+, and it tells you solid, solid. What's it solid in? It's solid when it's with this. It's insoluble in hydroxide. Do you see how it works? The chart? All right, so let's write that out. Make sure we have it written out. I'll give you a minute to write it down. Okay, raise your hand if you're finished writing, so I know when everybody's done. Okay, everybody's still writing it out. Okay, we've got it written out. I'm waiting to see all hands, so I know everybody has it written out. Okay, 1, 2, 3, 4. Got hands, got hands. There you go. Can you see better from there? Hands. So Na2CO3 aqueous plus FeCl2 yields FeCO3 solid plus 2 NaCl aqueous. All right. Okay, so I think just about everybody's got it. So now what are we going to do? We're going to break our reactants into their constituent ions. So how do we do that? We have a 2Na. Now notice what we've done. Because we're disassociating the ions from the compound that they form, we're going to change the subscript to a coefficient because it's by itself. Anything by itself has a coefficient. So do you see that Na2 became 2Na? All right, does everybody understand that that still means the same thing? It's still 2 sodiums, it's just now it's by itself. So because it's by itself, it gets a coefficient instead of a subscript. And the charge, how do we know that the charge on sodium is a +1? How do we know that? Where did we find it?
On the bottom.
Right here, sodium charges +1. Does everybody see how we did it? What's the next thing that's going to come out of here?
Carbon.
No, we're going to take out the ion, not the whole element. So the ion is going to be the carbonate. It's polyatomic, and here it is right here. So CO3, and the charge is going to be what? 2 negative. So it'll look like that. Now you see that the 3 is gone in the front, though, because once again, we need it to be a coefficient, not a subscript, because we have separated it out. Does everybody understand the separating it out part? You swap it from a subscript to a coefficient. Drew, are you writing it? Okay. Colin, are you writing it? All right. So then what's the next thing? We have to separate the iron and the chloride. So the iron is going to be a 2+. Why is the iron a 2+? Yes.
Chlorine is a -2.
Okay. Yeah, you could do it that way. Okay, because there's 2 chlorines and chlorine is -1 and there's 2 of them, you know, it's -2. That helps. You could do it that way. You could also look at like over here, but that might get a little confusing. So That's how you do it. If this guy is going to be, chlorine is -1, right? So if you don't know the charge on the other ion in your compound, if you know the charge on one, then you know the charge on the other. So if chlorine is -1, it's a -1 charge right here, and there's two of them, then this has to be +2, right? It's got to be. And now we're going to check our charges. So they look right. You have +1 and +1 and -2. Do we all agree that's going to balance out? We have +1 and +1 because we have 2 sodiums, right? And then we have a -2 for the whole polyatomic ion. We're not multiplying this times this. We're not getting 6. The whole polyatomic ion is a -2. And there we have +2, -1, -1. Do we agree that this must be right? Because these were uncharged ionic compounds, right? They were neutral when they were together. Okay, so now we're going to combine inners and outers. This is the easier part, inners and outers. Here's your outers, right? Our outers are sodium and chloride. What do? We're going to write them down here just like we wrote them above. So 2Na + 1 plus 2Cl - 1. There's your outers. I'll give you a chance to do that. And we're going to put them over here on the other side, on the outside, because there are outers. So then we've done the outers. What do? The inners. Okay. We also can write this as 2NaCl because we know we've got 2 sodiums and 2 chlorines. So our inners. What do we do for our inners? Our inners are Fe2 and 3CO -2, right? There they are. Why did we switch the order? Why isn't it CO? Because this 3CO -2 is over here. PJ, do you know, Yusuf? Metals come first. When you're naming a polyatomic, when you're naming an ionic compound, you always name the metal first, right? It's not chloride sodium, it's sodium chloride. So it's going to be iron what? Iron what? Carbonate. Iron carbonate. Very good. All right, so then you write it over there on that side. You're like, okay, looking good. How do we combine that? FeCO3. Because you had a +2 and a -2. Now you've got a neutral compound. Does everybody see that it's a neutral compound? All right, so now what do? This is our solid. How do we know this is our solid? Well, one way you know, sodium and chloride, we know that these dissociate in solution. You know that, right? You've done it many times. You've dissolved salt in water. But if you look over here, you see iron and then carbonate. Well, let's look. Here's the iron. And let's see, when it's combined with carbonate right there, it doesn't tell you anything, but that's still solid. It should just say solid again. So you can look on this chart and it tells you, okay? So that's going to be aqueous. We know it's going to be aqueous. So now how do we write the total ionic equation? Well, we do it like this. Here's our molecular equation, which is basically what you're starting with, right? Your sodium carbonate plus your iron chloride becomes iron carbonate and sodium chloride. There is your ionic equation. You see how we've broken each of these ionic compounds down into their constituent ions. Now we have to find our spectator ions. Yes. Yeah, I think there is one of these on the midterm. I think just one of these. I have to go and look. So locate the spectator ions. All right, where are they? Somebody tell me a spectator ion. What's one that we see on both sides of the arrow? Caitlin? What do you say? The sodium, the 2Na+1, is he on both sides? He's just hanging out, right? He's not doing anything. And this guy right here, like it's broken apart. But remember in the other video, it said you don't have to break those apart. We know that this is one. It's solid, so it stays solid. So we could have written that as one. So yep, sodium's gone. What else is gone? We're gonna lose something else. Jordan?
Yeah, it's C, chlorine.
The chlorine's gonna go away. Okay, so those are our spectator ions. So now we write the net equation, and it looks like that. right? Carbonate plus iron, iron carbonate. Got it? Getting there, clear as mud. Let's try another. All right. Here's our information again. Here's our equation. All right, I'm going to give you a minute and see if you guys can break those down into their constituent ions. So it's 2 LiOH aqueous plus Liam plus 2 LiCl. Oh, I'm sorry. 2 LiOH aqueous plus BaCl2 aqueous yields 2 LiCl aqueous plus Ba, and then in parentheses, OH, then the 2 aqueous. Lucas, you writing it out? Working it out? Drew, you working it out? Colin? Okay, so we're breaking that down into all the breaking the ionic compounds down into their constituent ions. Giving everybody a minute to see if they can get the first step on their own. Ah, she says, oh no.
What even is Li? Is that lithium?
Lithium. Mm-hmm. Lithium's right here. Charge of +1. OH. That's a polyatomic ion. You can find it right here. Anybody know what OH is called? That's hydroxide. Acids contain hydroxide ions that will dissociate. That's just the way that, I mean, I don't, that's always that way. Yeah, OH is always that way, hydroxide. I'm
They made it
sure there's a reason that I'm not coming up with at the moment, but yeah.
science. Science.
And then barium. Here's barium. It's got a charge of +2. Chloride we know has a charge of what? -1, because it's a halogen. All our halogens are -1. All right, so here's how that looks. 2 Li plus 1. Be sure you have that. Plus what?
2.
Anybody want to guess? 2 OH what? Yeah, she's got it. 2 OH -1. If it just has a minus, it's a -1, right? Very good. All right, PJ, good. Plus what? Barium is going to be what? Here it is. Yep. Ba +2. And then what are we going to do with this chlorine, with chloride here? What happens to the 2? It's no longer, Liam, it's no longer a subscript. It becomes a coefficient. And what's the charge for chlorine? -1 plus, there you go. All right. Are we following? Are you writing along back there at the back table? All right, check our charges. We have, yep, +1, +1, because there's 2, -1, -1, because there's 2, that's neutral, we're good. Ba +2, Cl, there's 2 of those, so it's gonna look like that. Those are good, all right. We know that we've gotten those correct so far. Combine our inners and outers. All right, first thing we're gonna combine are our outers. So what do lithium and chlorine make together?
Lithium chloride.
Lithium chloride. So how do we do that? We have 2 lithium chloride with a +1 charge and 2 lithium, sorry, with a +1 charge, and 2 chloride with a -1 charge. And then our other outer over here, I should have had that little line. I don't know why I didn't draw that little line. That came early, that animation, sorry. So 2 lithium chloride, because that's how we know they're just going to combine evenly, right? Right. So then plus our inners. All righty, what are we going to get for these? What you get? Barium and hydroxide. Yep. So how are we going to do it? We're going to write it down like this. These were just going left to right. They could go, you could switch them the other way because you're going to end up writing it the other way, right? You're going to end up writing it barium, hydroxide, right? Instead of hydroxide, barium. Nobody does that. So here's your 2OH with a -1 charge and your Ba with a +2 charge. That's going to give you BaOH. Got it? All right, now, lithium chloride. Is lithium chloride going to be soluble or insoluble in an aqueous solution? Insoluble? Soluble? What do we think? So here's your solubility chart. Do we see anything over here that might be helpful? Here's lithium. SOL is soluble. I think I read solid in last time, but it's soluble. SOL is soluble. If it's blank, that's what I did wrong. If it's blank, there's not enough data, or it's probably going to be a solid. SOL is soluble. So here's your lithium here. When you combine it with chloride down across, you get what? Soluble, right? Soluble. So your lithium chloride is soluble. Is your barium hydroxide going to be soluble? Here's your barium. Here's your hydroxide. Oh, what's happening? Aqueous. Aqueous. Oh. Oh. So it's a different type of reaction. So this is your full reaction. Now, here's a question. If it's soluble, everything is soluble. Everything is aqueous. So what does that tell us about our spectator ions? Have a look. Where are our spectator ions?
They're all spectator.
They're all spectator ions. There's lithium. There's chloride. There's hydroxide. There's barium. So they're all spectator ions. In this case, we didn't get any sort of, no, we don't have a net ionic equation. They're all spectator ions. They're all soluble. They're all spectator ions. No biggie. All right, so here's a couple other samples. So for this one here, if we write our complete net ionic equation, give you a chance to see if you can get to it on your own. So you're breaking NH4, 2 from your carbonate, aluminum, nitrate. And this tells you already what its state is. So you know this is going to be your your precipitate, right? All right, so this is what you're looking for. We've broken out. This is ammonia. This is carbonate, aluminum, nitrate. Then you got ammonia, nitrate, aluminum, and carbonate. So where are our spectator ions? What do we see? Here's the solid, and it's all together, so we don't need to mess with it. So do we have an NO3 on both sides? Yeah, we do. 6 of them on both sides. How about the NH4? Do we have that on both sides? Okay, so those are going to be our spectator ions. We're going to get rid of them. So we have 2 Al3 plus aqueous gives us 3 of these carbonates, and they're 2 negative. So are our charges correct here? 3 times -2 is -6, right? 2 times 3 is 6. 6 and -6 balance out. Right, so we know we're good. Whoop. let you try that next one for a second. See if you can figure it out. Guys in the back, stop chatter. There was a practice. Guys. Somebody's important. My dad is.
Hello? Yeah. Okay, thanks very much. Bye-bye.
All right, so here's what we got. There's our complete ionic equation. We've broken it down into our sodiums, our hydroxides, hydrogen ions, and what's SO4? Sulfate. Real good, real good. And then over here we got sodiums and sulfate and then water. Okay. Now, what is this? What's this here? It's not actually a 1. It's an L. Why is it an L? Yeah, okay. Because all of these are aqueous, which means they're dissolved in a water solution. But this shows that it is water in what state? Liquid state. Right, okay. Not water in a gaseous state or water in a solid state, but a liquid water. Do you understand, back in the back, the difference between aqueous and liquid? Bless you. Do you understand? Aqueous means it's dissolved in a water solution. Liquid, in this case, means the water is in its liquid phase, right? So then our net equation, what did we get rid of? Sodium on both sides, he can go away. Sulfate on both sides, he can go away. So we had hydroxide and hydrogen, which gave us water. And then you get some of these dissociated and then water on its own. All right, cool. Try another one. This one's smaller. Magnesium and hydrochloric acid. Give magnesium chloride and hydrogen. This one on the top. Everybody try it, even if it terrifies you. Making mistakes is how you learn, right? You do it wrong, you learn how to do it right. If you don't make a mistake, you didn't learn anything because you already knew it to begin with, right? That's how it works. So what are we breaking apart? The hydrochloric acid and the magnesium chloride. So how does it look complete? It should look kind of like this. Your magnesium is still on its own, right? Which when you break up the hydrochloric acid, your hydrogen's a plus, your chlorine is a negative. You got 2 of each, right? Over here, you've got your magnesium, which is a 2 plus, and then you have 2 of these chlorides, and then you've got this hydrogen all by himself over here. What state is the hydrogen in?
Yeah.
Gas. So what's going to happen if you put magnesium into hydrochloric acid? What should you see? You should see bubbles, right? You should see bubbles forming. So what are we gonna get rid of? What are our spectator ions?
Who's the chloride?
Yeah, we're getting rid of the chloride because it's not doing much here. So we have our magnesium, which is gonna stay a solid. Our 2 hydrogen, and that's gonna give us, there we go, magnesium in an aqueous state and hydrogen. How about this next one? Solid zinc, copper 2 sulfate, copper 2 sulfate. Again, here it is, right? We keep using copper 2 sulfate. And then we end up with zinc sulfate and copper. See if you can break those apart. By the way, while you're working on it, here's our updated situation with this guy. Yeah, I'm going to next week. It's going to be a requirement. Yep, that's coming. Donuts and marshmallows don't help. Shh, Liam, Andrew. You should be trying this. Shh, nothing. Yeah, come up if you can't see. So we have solid zinc that we're putting in a copper 2 sulfate solution. And then we have zinc sulfate in solution, and solid copper is going to crash out. What do we call it when something forms in a solution that's a solid? Precipitate. It's going to crash out of solution. So what we should have is this. There's your zinc. Your zinc, your copper 2 sulfate is going to dissociate as shown. Then you're going to have zinc sulfate and copper. Where are spectator ions? Sulfate. Everything else is doing chemistry here, right? Because look, even though you have copper and zinc on both sides, you have copper ions over here. And then elemental copper over here that's not in an ionic situation. And then the zinc over here was elemental zinc, not an ion, but it's going to turn into a zinc ion on the other side. So when you get rid of the sulfate, there's your net ionic equation. Zinc solid and zinc 2+ are not the same. One is elemental while the other is a monoatomic ion. Same applies to the solid copper and then the copper ion. Right on. Okay, let's look at our answers from our binder work. So can someone tell me what are spectator ions? How do you define them? Caitlin?
They are,
Okay. Crash. We got it. Okay.
in a reaction that don't interact with.
Yes. They're the ions that don't do any chemistry. They remain in the solution while the reaction's taking place, but they don't take part in the reaction, right? Right on. So does anybody have the total ionic equation for each of these? Total, not net. All right, Jordan, what do you have for A?
Cu2 plus
Mm-hmm.
plus SO4 2 minus.
Yes.
Fe
Yes.
Fe3 plus.
Right.
Plus C.
Okay. So this is what you should get. You got 3 if you were to do it as, so it gave you the chemical name. So from that, you needed to know the equation. So first thing you have to do is kind of balance it out to make sure you know what your coefficients are going to be. Because just saying copper 2 sulfate, we know that CuSO4, but how many of them are going to be in this equation? So this is like a 2-step deal, right? You got to balance it to get your coefficients correct. And then you break it down into your net ionic equation. So what I'm gonna do is I'm gonna put the next one up so you can check it against your work.
What? I got one mistake. I put a pluses and minuses.
Ah, that happens.
Is the one after the K a plus or a minus? I can't see.
This is a plus,
Oh, yeah.
plus, plus, right? Plus, plus. So how many of you did it without balancing it first to find your coefficients? Yeah, everybody. Yeah, you gotta know how many you're working with. Because it's one thing to read out a reaction. You would read it out as just potassium iodide and chlorine make or yield potassium chloride and iodine. But you have to be able to do that first step, our marshmallow trick. You have to balance it out first so that you know what you're doing. And we may have something like this in a lab or whatever, but you're not going to see usually the two-step ones like this too much on at least too many of my tests or midterms or anything. I don't think there's one like this. I'll have to double check, but I'm pretty sure there's not.
Give me the
Starting with the balanced equation, I think there is. Yeah, I'd have to double check, but I think there is one that's on there that starts with the balanced equation. That I try to make the ones that are like that light on points because I'm more for make sure you have your big ideas and you know how to do stuff. I do expect you to know how to balance. You're going to have to know how to balance, and you're going to have to know, like, if you go through this and it tells you stuff in here, like, oh, look, percent composition. You're going to have to know how to do percent composition, right? Which was last week's lesson. 2 weeks ago lesson. Yeah. So here's what ones that you can practice balancing. Right. Pretty much if you know how to do everything in there, and then in the Jeopardy, have y'all found the Jeopardy yet?
Yeah.
Yeah. All right, here's what the next one looks like. And I'll put these next few up, and you be sure that you've copied your correct answers so that you know you've got your right answers with you, so you know how to do it. If you go back and check your work. And you guys know that this, you can find this slideshow in your Dropbox, right? And then you can also find the video in the class YouTube. So if you need to go back and look, you can go back and look. All right, so for letter A, what are our spectator ions? What do you have, Jordan? The SO4. Yeah, the sulfate's going away. So the SO4 is our spectator ion. How about for B? All right, PJ? The potassium, she says. There you go. Yep, you got it. How about for letter C? What do we have, Caitlin? There you go. Yes. Oh, the SO4 too, right? Right here. They're in their second one. Oh no, because your magnesium is a solid and then it's aqueous. So yep, sorry. That's going to be your sulfate. You got to watch the state. All right. And how about D, Jordan?
NO3
Nitrate. Yep, you got it. Your nitrate. How about for E? What do we have? Yusuf?
bromine.
Bromine, aqueous. Okay, that looks good. That looks good. All right. And then how about for F? Anybody have F? PJ?
The copper.
Copper. Okay.
Chlorine.
Copper and yeah, and your chlorine, right? Is that not? Oh, I didn't put it in there. Should have been there. Yep. You're right. Okay, so here's what we're gonna do. I'm gonna put this up on the counter so that everybody can get a really good look at this. Something to tell you first. I think Tinker Day pictures from almost everybody, so that's good. So everybody will get some bonus. It will be in your email, your weekly email this afternoon, but there is one more midterm extra credit point opportunity And it's a digital virtual escape room activity where you balance equations to get out of an escape room. It's fun.
How many points?
Two, I think it
I'll
was.
do that.
So. If you combined all your Tinkerday credit and all of your, listen,
I
when,
didn't get a.
listen, when you combine. Listen, when you combine Tinkerday extra credit with escape room extra credit, you can't have more than a maximum of what on any test or midterm? 105%, whatever that works out to be, 105%.
So I can get 105%.
That's as high as anybody can get on anything is 105%. So give that a try. Next week, I want everyone to pick a new seat, not next to the people you chatter with. I'm going to give you the opportunity to do that. If you don't chatter with people, you're fine. But if I've had to say shush to you or call your name, you're going to need to find a new seat and you know who you are. If you don't find a new seat on your own next week, I'll assign you one, which is kind of embarrassing when you're in high school and you're old enough to find a seat on your own and not distract everyone else in the room. Understand? Yes, because chemistry gets hard and challenging for some people, and it really helps if we can focus. Okay, you're gonna take your marshmallows home. I don't care if you eat them or practice with them. Like I said, if you're a girl or you know a girl, take one of the Holland's packets. They're great. They sent them to me. Questions, PJ?
I'm gonna throw my marshmallows at Alex.
You can throw your marshmallows at Alex. I give you permission. You can tell them, Alex, this is from Miss Danny, and then pelt him. Tell him I love and miss him and enjoy. So anyway, real quick, this is where we ended up. Whoa, right? All right, I'll put this over here. Oh, wait, Daddy has a question for you. Shh, shh, shh. All right.
Y'all learned this in the first grade. And somebody issued an answer. If I got 2 nickels in my hand, what kind of fruit is that?
What kind of what?
Fruit.
A pear.
Hey, you knew it.
Oh, you were the last one.
It's a pear.
Yep. It's
Well,
okay.
you want a pair of shoes.
Yeah,
You can go home, take parents.
there you go. Share any other clean ones you would like. You may. Excellent. All right, I'll put your coins up on the counter. Here we go.
divide my coins up.
There you go. Gender.
It's not able to.
Okay. Yeah, that's fine. Make sure you turn in your mnemonic device for your 11 credit for last week, right? Don't forget that. Like this. Here, did you see it?
Yeah.
And against the white.
Yeah.
Andrew right there. He answered it.
Which one?
Can see the little sparkles. Isn't that cool? You can do it under a microscope and really see it, but this is better to like pass it now. But it's pretty cool. You can see it change color, solutions blue. Look how hairy that is. Isn't that wild? And this is what comes out of it. That's the silver I got.
You can just throw it over and make money.
You can just grow silver. Yep. Just straight grow it.
It's like an exact money.
Yeah, kinda. Kinda. Alright, y'all.
You don't want my coin on the.
Is that your mnemonic device? or
It's
your lab?
valid.
Oh, yeah, lab 11.
Put it
Yeah,
on
you're
the-
in- put it-
One donation.
You can put it on that. That's totally fine. Or you can throw it on a separate sheet of paper. It doesn't matter to me.
You're on Cleveland, or on take your lunch.
No, it's really easy. I got it done. I do it every week, so I've gotten pretty quick at it.
What'd you say?
I said I do this every week, so I've gotten pretty quick at it. cleaning up. So monsters come in here and some of them are very messy. Some of them are not, some of them are real messy people. Leave stuff everywhere. Yeah, that I got you to, it's pretty cool, isn't it? Really.
It's a bit.
It's sparkly, it's sparkly.
Yeah, but I want to.
You know, tasty, good. I don't feel like taking anybody to the hospital today. It's not on my agenda, thank you very much. I have other things to do.
Wait, so if gold, how is gold leaf made edible?
It's just gold that's hammered out really, really, really thin. Keep it quiet by the front door. Thank you. Some people erase their marshmallows. That is gross. Oh, black shriveled up marshmallows. Ew. Yuck. Alright, let me end this recording.
Is there